Welcome back. In the last video, we discussed some basic tensor operations, such as addition, subtraction, multiplication, element-wise, division, and matrix multiplication, but we didn't actually go through what matrix multiplication is, so now let's start on that, more particularly discussing the difference between element-wise and matrix multiplication. So we'll come down here, let's write another heading, matrix multiplication. So there's two main ways, let's write that. Two main ways of performing multiplication in neural networks and deep learning. So one is the simple version, which is what we've seen, which is element-wise multiplication. And number two is matrix multiplication. So matrix multiplication is actually possibly the most common tensor operation you will find inside neural networks. And in the last video, I issued the extra curriculum of having a look at the mathisfun.com page for how to multiply matrices. So the first example they go through is element-wise multiplication, which just means multiplying each element by a specific number. In this case, we have 2 times 4 equals 8, 2 times 0 equals 0, 2 times 1 equals 2, 2 times negative 9 equals negative 18. But then if we move on to matrix multiplication, which is multiplying a matrix by another matrix, we need to do the dot product. So that's something that you'll also hear matrix multiplication referred to as, the dot product. So these two are used interchangeably, matrix multiplication or dot product. And if we just look up the symbol for dot product, you'll find that it's just a dot. There we go, a heavy dot. Images, there we go, A dot B. So this is vector A dot product B. A few different options there, but let's look at what it looks like in PyTorch code. But first, there's a little bit of a difference here. So how did we get from multiplying this matrix here of 1, 2, 3, 4, 5, 6 times 7, 8, 9, 10, 11, 12? How did we get 58 there? Well, we start by going, this is the difference between element-wise and dot product, by the way. 1 times 7, we record that down there, so that's 7. And then 2 times 9, so this is first row, first column. 2 times 9 is 18. And then 3 times 11 is 33. And if we add those up, 7 plus 18 plus 33, we get 58. And then if we were to do that for each other element that's throughout these two matrices, we end up with something like this. So that's what I'd encourage you to go through step by step and reproduce this. A good challenge would be to reproduce this by hand with PyTorch code. But now let's go back and write some PyTorch code to do both of these. So I just want to link here as well. More information on multiplying matrices. So I'm going to turn this into Markdown. Let's first see element-wise. Element-wise multiplication. We're going to start with just a rudimentary example. So if we have our tensor, what is it at the moment? It's 1, 2, 3, and then if we multiply that by itself, we get 149. But let's print something out so it looks a bit prettier than that. So print, and I'm going to turn this into a string, and then we do that. So if we print tensor times tensor, element-wise multiplication is going to give us print equals, and then let's do in here tensor times tensor. And we go like that. Wonderful. So we get 1 times 1 equals 1. 2 times 2 equals 4. 3 times 3 equals 9. Now, for matrix multiplication, PyTorch stores matrix multiplication similar to torch.mul in the torch.matmul space, which stands for matrix multiplication. So let's just test it out. Let's just do the exact same thing that we did here. Instead of element-wise, we'll do matrix multiplication on our 1, 2, 3 tensor. What happens here? Oh my goodness, 14. Now, why did we get 14 instead of 1, 4, 9? Can you guess how we got to 14, or think about how we got to 14 from these numbers? So if we recall back, we saw that we're only multiplying two smaller tensors, by the way, 1, 2, 3. This example's with a larger one, but the same principle applies across different sizes of tensors or matrices. And when I say matrix multiplication, you can also do matrix multiplication between tensors. And in our case, we're using vectors, just to add to the confusion. But what is the difference here between element-wise and dot product? Well, we've got one main addition, and that is addition. So if we were to code this out by hand, matrix multiplication by hand, we'd have, recall that the elements of our tensor are 1, 2, 3. So if we wanted to matrix multiply that by itself, we'd have 1 times 1, which is the equivalent of doing 1 times 7 in this visual example. And then we'd have plus, it's going to be 2 times 2, 2 times 2. What does that give us? Plus 3 times 3. What does it give us? 3 times 3. That gives us 14. So that's how we got to that number there. Now, we could do this with a for loop. So let's have a gaze at, when I say gaze, it means have a look. That's an Australian colloquialism for having a look. But I want to show you the time difference in, it might not actually be that big a difference if we do it by hand versus using something like matmul. And that's another thing to note, is that if PyTorch has a method already implemented, chances are it's a fast calculating version of that method. So I know for basic operators, I said it's usually best to just use the straight up basic operator. But for something like matrix multiplication or other advanced operators instead of the basic operators, you probably want to use the torch version rather than writing a for loop, which is what we're about to do. So let's go value equals 0. This is matrix multiplication by hand. So for I in range len tensor, so for each element in the length of our tensor, which is 1, 2, 3, we want to update our value to be plus equal, which is doing this plus reassignment here, the ith element in each tensor times the ith element. So times itself. And then how long is this going to take? Let's now return the value. We should get 14. Print. 14, there we go. So 1.9 milliseconds on whatever CPU that Google Colab is using behind the scenes. But now if we time it and use the torch method, torch.matmul equals tensor.tensor. And again, we're using a very small tensor, so okay, there we go. It actually showed how much quicker it is even with such a small tensor. So this is 1.9 milliseconds. This is 252 microseconds. So this is 10 times slower using a for loop than PyTorch's vectorized version. I'll let you look into that if you want to find out what vectorization means. It's just a type of programming that rather than writing for loops, because as you could imagine, if this tensor was, let's say, had 1 million elements instead of just 3, if you have to loop through each of those elements one by one, that's going to be quite cumbersome. So a lot of PyTorch's functions behind the scenes implement optimized functions to perform mathematical operations such as matrix multiplication, like the one we did by hand, in a far faster manner, as we can see here. And that's only with a tensor of 3 elements. So you can imagine the speed ups on something like a tensor with 1 million elements. But with that being said, that is the crux of matrix multiplication. For a little bit more, I encourage you to read through this documentation here by mathisfun.com. Otherwise, let's look at a couple of rules that we have to satisfy for larger versions of matrix multiplication, because right now we've done it with a simple tensor, only 1, 2, 3. Let's step things up a notch in the next video.